Hello, everybody. So, today we're going to talk about observing Tokio and how you can shine a light into your async runtime and your own async program as well. So, who am I? My name's Hayden Stainsby. I'm an engineering manager at Here Technologies. I work with a team that serves real-time traffic data to end-user devices, so we do that with pretty low latency. Sometimes we even do it with Rust. I'm also on the Tokio RS maintainer team. So basically what happened was I was a really content, happy even, no coding manager until we started using Rust. And now I find myself writing Rust.code tests and all sorts of other stuff in my spare time. Let's be friends. I'll have links at the end of the talk as well if you want to download the presentation, but email and website, GitHub, Mastodon, if you're interested. And latest thing, I started a...
Monitor covers your face.
Okay, I actually can't because it doesn't go down.
Oh, okay.
Hang on,
So,
can we move this so I stand like to the side?
Oh, yeah. Can people still see that? Just rotate it.
This? The whole thing? Yes. Oh, look at that. That was a good idea. Right, now I can be seen. Okay, so I started a lunchtime virtual Rust meetup because I don't have time in the evenings when most meetups are. So if you want to spend like an hour listening to some Rust talks, the next one's on Tuesday. Lunch.rs should be pretty easy to remember. Right, what we are going to talk about today, a little bit of context just to sort of put us all on the same page. I'm going to introduce Tokio for those of you who aren't super familiar with it, although to be fair, this is probably going to be the third or fourth time that somebody's introduced Tokio so far in the conference, so I suppose maybe not everybody's seen all the talks. Then we'll go through the 3 observability tools that I'm going to present, Metrics, Tokio Console, and TaskDump. And then I'll give a bit of my idea about the current state and the future. And for anybody downloading the PDF, which I'm sure will be available later, I put all of the links that appear throughout the presentation also at the end, so you can just jump down there and grab them all rather than having to hunt through the slides for it. I won't show that though. So first, a little bit of context. I wasn't sure where to start, so I thought I'd start at the beginning. Rust is a language empowering everyone to build reliable and efficient software. But we're at RustLab, right? So that's probably enough for everybody. Async or asynchronous programming, I will be calling it async programming for the rest of the talk, is a concurrent programming model. So for those of you who are not, let's say, using so much async, what's the difference between parallelism, traditional thread-based or multi-core programming, let's call it. So parallelism is when you're doing many things at the same time. Concurrency is when you wait for many things at the same time. I heard James Munns say that most recently, although he said that it was said by somebody else before him, so who knows who said it first. What this really means is that you can take single core and you can interleave tasks onto it. You can also take multiple cores and interleave tasks across multiple cores. It works just as well. The basic unit of concurrency is a task. This is fairly standard nomenclature, but definitely within Rust, this is the standard. You can run, and this is the idea, you can run many, many tasks on fewer OS threads. And often, and definitely in the case of Rust async, scheduling is cooperative. That means that different to when you're running parallel programming, sort of sorted out by the operating system, we have multiple threads. The operating system can yank a thread off its core whenever it wants to and put it back either onto the same core or a different core, which causes all sorts of wonderful problems for your cache. The concurrent programming in Rust, and in a lot of other places as well, is cooperative. That means that the runtime can't yank your task, aside from a couple of exceptions, away from what it's doing. The task has to decide to yield back to the runtime. We'll go into this a little bit later on, but this introduces all sorts of opportunities for tasks to misbehave, which is perhaps one of the biggest problems that we see. So, how does async work in Rust? Rust provides some async definitions, so the concept of a task, a waker we'll look at a little bit later. We have async await syntax, which makes things much easier to write since 2019. There's no async runtime. And I think Antonio mentioned this yesterday, I think it was, but this means you get to pick your own. So Tokio is the one that I'm going to talk about today. Async Standard and Small are two other async runtimes which are fairly general purpose. Then you've got more specific ones, such as Embassy, which is for embedded devices. It's pretty likely that you're using Tokio. And I noticed that a few other talks have been discussing using Tokio as well. You might be using something else, but today I'm talking about Tokio. Async Rust can be tricky. So the cooperative scheduling that I mentioned before is fine until someone doesn't cooperate. The async await syntax gets converted down into futures at compile time. Actually, debuggers are usually pretty good at putting that back into async syntax when you're running through a debugger, but the stack traces aren't so meaningful. The debugger overly affects what you're doing, similar to parallelism, but worse, or maybe the same as parallelism because you're probably running multi-core anyway, just with added stuff on top. And sometimes your application just hangs and you don't know why. So async Rust is hard. This was like the premise of my talk. Stop. Async Rust is hard. Didn't we see this yesterday? So Antonio Scandura stole the premise of my talk. Clearly this slide wasn't in there until I saw the talk yesterday. Property testing async code in Rust was a fantastic talk. And got me thinking about a bunch of stuff. So it's the perfect companion for what I'm going to show. In the Rust world, or let's say following Rust principles, it's probably the better idea if you can, because it happens earlier on. He talked about testing async code. I'm going to talk about how you can take the code which you may or may not have tested and work out what's going on afterwards. So sure, test it first, but maybe you didn't, or maybe the testing missed something, and I'm going to show you how to, go on with that. So back to our regularly scheduled programming. Async Rust is hard, or to be fair to Rust, async is hard in general. It's not Rust's fault. So what? What do we do? Luckily, we have something that most Rust applications don't have. We've got superpowers, which actually we have a runtime. Remember, Rust doesn't have a runtime, except if you're doing async, you need a runtime. So now we have a runtime. This is where we can put our observability. What's observability? If you look this up on Google, you usually see the 3 pillars of observability are logging, metrics, traces. But I much prefer this definition from the Observability Engineering book, which is observability is a measure of how well you can understand and explain the state of any state that your system can get into, no matter how novel or bizarre. Do we have this sort of full observability in Tokio? No, not yet. But we might have more than you think. So, bit of an introduction to Tokio now. Tokio is a runtime for writing reliable, asynchronous, and slim applications with the Rust programming language. This probably applies to a lot of other async runtimes for Rust as well, although latest tests probably show that slim is the place where, maybe embedded aside, Tokio really shines. So Tokio is a popular async runtime, probably the most popular async runtime for Rust, but I'm also biased. It drives the task scheduling and execution. It handles cooperative scheduling, which means that inside some of the resources that Tokio provides, it will check whether you're perhaps blocking unintentionally because whatever you're waiting on is always ready, which also presents problems. It also has work stealing, so if you have a multi-threaded or multi-core async runtime and one of your workers, that's not me, I can see it. But if I turn my computer around, it's too small.
Now you do math and you just keep going.
Yeah. I'll go running up and down the aisles. Yeah, I think somebody might be coming. It's just turned off. It's fine. It's fine. No?
Maybe the cable.
Cable?
Try to...
Hang on.
Yeah.
We're going to turn it off and turn it on again. You can tell I started in IT support. Hey, there we go. So, where was I? Work stealing, right. If your Tokio runtime is running on multiple cores and one of the workers are core bound or thread bound, whatever, one of the workers runs out of work, it can go and look in the local queue of some other worker. There's a global queue, but maybe that's empty as well. It can look in the local queue of some other worker and steal the work. It steals half the work, which is interesting. And the task, as I said, a low overhead. So I have this number of, tasks have roughly 88 bytes of overhead. I haven't checked this recently, but it's more or less that. So a task will basically weigh in at 88 bytes plus the size of your future. What else does Tokio have? Tokio has timers, so for sleeping and so on, synchronization primitives, which are similar to the ones in the standard library, but async, so mutexes and what else? Read-write locks and so on and so forth. Networking and file I/O, which if you're doing network applications is really important. Message passing channels, so we saw that in Yuka's talk before, like we've got multi-key processor single consumer channels and broadcast channels and so on, which are all async. And aside from being sort of integrated into Tokio, they also provide this cooperative scheduling, like co-op budget. So we've got the kitchen sink. Well, we'll call it batteries included. Tokio also has instrumentation built in, which is the whole point of this talk after all. Tokio has metrics built in. There are traces using the tracing crate and task dumps. And this is going to provide the observability that we need to work out what's going on in our async applications using Tokio. So first, a little bit the elephant in the room. Most of the tools in this presentation require Tokio unstable APIs. Unstable doesn't mean untested, although probably yet less used because you have to enable it sort of manually. But it does mean that the APIs may break outside of major version bumps. That's the most important thing here, and the fact that you have to enable it. I know of larger companies that are running Tokio unstable in production with like enormous amounts of traffic. So it's not that it can't be done. You probably want to be a little bit more careful. So how are we going to enable that? You need to set your Rust flag and config Tokio unstable. You can do this with an environment variable, or my preference is to put this in your .cargo/config because Rust Analyzer will pick it up in your IDE of choice, whereas the environment variable is much harder to get to Rust Analyzer, at least in my experience. And this will set it. You can even check it into your repository, and then everybody else gets it in the case that whatever you're writing needs these unstable APIs. So first of the tools that we're going to talk about are metrics. So metrics are counts or measures aggregated over time. Tokio has runtime metrics, which are sort of aggregated at the runtime level. And additionally, there is a Tokio Metrics utility crate, also from the Tokio team. I think it was originally started by Jack Wren, and I know Noah Kennedy's contributed to it quite a bit as well. And this adds some additional functionality which you can use alongside or on top of the metrics from Tokio itself. So the runtime metrics, which are built into Tokio, are available from the runtime handle. We'll see how to do that in a sec. There are 25 of them, including your active task count, poll time, histograms. So very, very quickly, we talk about when a task is busy is when it's being polled because of the poll function on the futures. So I'll be using polling mostly, or poll times, worker metrics for each of the workers in a multi-threaded runtime, IO driver metrics, and much, much more. So how do we actually get these out? The important stuff is here where we grab our runtime handle and we can get the current one if we've gone into with the Tokio main macro and grab the metrics off it. Once you've got this metrics object, you just pull the stuff out you want when you want, and that's it. So we have 10 active tasks here. If I pull it a little bit, if I call that a little bit later, there'll be less because they'll start timing out. There's a lot you can do there. I'm not going to go into all of the individual metrics because there are lots and I just simply don't have enough time. So we'll jump right into the Tokio Metrics crate. This provides patterns for monitoring tasks or the whole runtime. It gives you an iterator which yields metrics at intervals. So in this case, you get the metrics that have changed, like the diff of the metrics since the last call in most cases. This is really, really useful for preparing metrics for a collector, like Prometheus, for example. I'll give a bit of an overview of how you do that. Also, in the Tokio Utils crate, we have this task monitor. So this doesn't require Tokio Unstable. It's the only thing I'm going to talk about today that doesn't require Tokio Unstable. And what it does is it tracks key metrics of instrumented tasks. So you have to explicitly instrument these tasks. And you can have multiple monitors, and you can monitor multiple tasks with each monitor. So the idea is you probably want to use distinct monitors for different types of tasks. You have recorded metrics, for example, total poll count, the number of times that a task has been polled, so the number of times it's been woken up to work, total idle duration, derived metrics such as the mean scheduled duration, the mean fast poll duration. Scheduled duration is the time from when a task gets woken up until it gets polled. And fast poll time is interesting because in the Tokio Metrics crate, we distinguish fast and slow polls, where the default breaking point is at 50 microseconds, but that's configurable, and long and short scheduling delays. Again, the breaking point is at 50 microseconds, but you can configure that. So this means that you can answer questions like, are my tasks taking longer to poll? Are my tasks spending more time waiting to be polled? Are they spending more time waiting on external events to complete? And actually, it turns out that separating this into fast and slow poll times, for example, means that you can say, hey, do I have more tasks which are polling slow now than I did before? And so on. There is some incredible documentation on the task monitor. Jump through to this link. Jack wrote a whole debugging scenario with questions and answers and step-by-step that introduces you to a really large number of the metrics available. If you're interested in this, I would suggest that you check it out. You could make an entire talk from that page just by itself. But I didn't find it until after I submitted this talk idea, so maybe next time. So how do we use the task monitor? We create our task monitor. Here's the important stuff. And then we instrument whichever task we wish to instrument. And then we grab our intervals, and this is our never-ending, our never-ending iterator. And we just keep calling next on this at whatever interval we're interested in and pulling data out. Now you can pretty print this out and get all of the fields, or you can use this to respond to a metrics endpoint. So normally what you would do, and we'll see this again later on, you get call to your metrics endpoint, and you grab the next iterator for the next interval, and you spit that out. So runtime monitor is metrics not for specific tasks that you've instrumented, but now for the entire runtime. You don't need to explicitly instrument anything. It wraps Tokio's runtime metrics, and it does the same thing as the task monitor. So you get intervals for the metrics, you get also on top of that a snapshot for all of the metrics, whereas that requires a little bit more work from the base metrics from Tokio. And it also provides derived metrics like the task monitor does. So you can get also useful summaries of worker behavior, such as the max busy duration for a worker, mean poll duration of the worker that had the highest poll duration, which is a little bit of a mouthful, but can be useful. The min steal operation, so this is the worker that stole fewer tasks than any other worker, and max overflow count, which is when the workers have a local queue, and then there's a global queue when they're scheduling tasks for execution. The local queue is what a worker has, and that might overflow. So you might run out of space, and then the task needs to be put into the much slower global queue. So that's why this one's interesting. How do we grab the runtime monitor? Again, we get our handle here. We construct our runtime monitor, and then it's the same thing. So grab the intervals and keep calling that whenever you want to. As I said, I promised I would show you how to integrate this with Prometheus. These monitors, the runtime monitor and the task monitor, are easy to integrate with collectors. For example, the Prometheus crate, metrics crate as well, which I should be plugging because it's part of the Tokio ecosystem, but I haven't had so much experience with it. No bad experience, just not much experience. There is some boilerplating involved in this. So if you look here, for one single metric, I first need to register it. That I do once. And then when I get a call to my metrics endpoint, I will need to get my runtime metrics, and then I will need to set this metric from the runtime metrics. And I need to do that for every single metric that I'm interested in publishing. Which, yeah, look, I mean, this is something that somebody could abstract out into a crate, or maybe even a feature on the Tokio Metrics crate. Nobody's done it yet. Any volunteers? No, I didn't think so. No, come talk to me afterwards, really. Pretty graphs. I'm not going to go into this, but basically you stuff all these metrics into Prometheus. It makes it very easy to then query them from something like Grafana and get your alerts on that if that's something you're interested in, and learn a lot more about what your async application is doing. So, what have we learned about about metrics in Tokio? They're available from the runtime handle. They can be exposed to tools such as Prometheus. We have task metrics for targeted instrumentation. You don't need Tokio Unstable for this. They're lightweight, and they're definitely suitable for using in production. On to tool number 2, Tokio Console. This is a diagnostics and debugging tool for async Rust programs built on top of Tokio. It's the rest of it. So it's built on the tracing instrumentation, which is in Tokio. This came out of some ideas from Felix, I can't remember his surname, and then I think there was a Google Summer of Code, and then the current implementation was mostly started by Eliza Weissman, who you've probably all heard of from the creator of tracing, and she also wrote most of the initial instrumentation in Tokio. So, credit where it's due. I'm trying to sort of actually say who's come up with this stuff, because I didn't build any of this stuff, but it's fantastic that it already exists. So, Tokio Console is sort of made up of 3 parts. There is a subscriber. This collects and analyzes the traces, which are in Tokio, from within the target application. So this is something that you start up like a tracing subscriber. Well, it is a tracing subscriber inside your own application. There's the console. This is a terminal application, which allows you to visualize and explore the state of the runtime. And then there's the API, which allows them to communicate. So there's a gRPC API, which defines the communication between the subscriber and the console itself. So basically, when your application starts up instrumented with console subscriber, it will be listening on a port for gRPC and going from there. So how do we add this in? You add it to your crates.toml, easy. If you're not using tracing yet for anything else, super easy, you just call console subscriber init. This will start up the subscriber, which is going to be listening for the tracing information, and on a separate runtime, not on your own runtime, on a separate runtime, it will spawn the gRPC server and some of the aggregation work that goes on. If you're already using tracing subscriber, it's also easy, fine. Whoops. So you're probably going to need your tracing subscriber prelude if you're not using it before. You set up whatever other layers you want to set up, and then you set up your console subscriber layer. It has a builder, and you can configure it this way, and so on and so forth. And then you put everything that you want into your tracing subscriber registry. So this is standard tracing subscriber stuff. If you've not done it before, for instance, if you're just using like tracing subscriber format init, or whatever it's called, to spawn the console output, then you're going to need to use a format layer instead of the format subscriber. It's exactly the same thing, and what the subscriber uses underneath. Yeah, don't this prelude thing, just stick it in. There's some trait stuff in there that will make it all work with the registry. Don't think about it too much. Right. On to actually using the console. So you can install it from Cargo with cargo install Tokio Console. Don't cargo install console, which I did the very first time I tried to use it, because that's something else entirely. Then you run it from the command line, also Tokio Console. And for the best experience, you want to make sure that you've got UTF-8 support, not just that you have it, but that it's in your Lang environment variable, or you can pass it straight to Tokio Console, and then you get pretty colors, and you get lines, and so on and so forth. It's a terminal application, but you need to tell it that you're happy with UTF-8 use. So here it is. This is the task list. Tokio Console really has sort of 2 sides to it. It has a tasks and resources, where tasks are tasks and resources are things like timers and sleep and semaphores and mutexes. It doesn't have, like, we don't have instrumentation for channels. It just hasn't been done yet. So that's something coming in the future, hopefully. But you can sort of look at that. Today, I'm only really going to look at the tasks. I think it's the easier thing to understand and plenty enough for the time slot I've got. So what have we got in our list, which, yeah, you probably can't read. So we get task ID. This is the ID you can also get from Tokio, so you can match it up. The state, whether it's paused or running or stopped or scheduled, which you can't see here. Take this with a grain of salt because we're publishing this, I don't know, like every 2 seconds or something, and 2 seconds is a really, really, really long time for your async program. So if it says it's running, it just happened to be running when we took the snapshot, unless it's running for a really long time, and then you'll notice. So we have our timings here, the total time the task has been alive, and then a split into busy time, scheduled time, and idle time. As I said before, so busy time I think is obvious. Scheduled time is the time between a task being woken and it actually being polled the next time on the runtime. And idle is the rest. The number of times the task has been polled. The kind of the task, I'm cheating here. The kind column you will see in the current version of Tokio Console in the fields over here. Not here, but we switched target and fields around because the kind is shorter, and that's really important in terminal applications. And it's more descriptive as well. So you don't see it here, but you'll see block on kind tasks and blocking tasks and local tasks as well. And then you get the location where the task was spawned from in your code, not in Tokio code, and any extra fields. So for blocking tasks, you'll also get like the function signature, which was passed to block on, and cool. We don't do that for async tasks because the function signature for async tasks, because closures and stuff can get really, really, really long and basically just kill the memory in your whole application, which you don't want. Because that happens in the console subscriber, not in Tokio Console here. Well, it happens in console as well. So basically it blows out the memory, and console subscriber uses enough memory as it is. There's the location, the fields, but we've got this gap here with the name. It's empty. What's going on there? Okay, task names. The Task Builder API in Tokio, another unstable friend, allows you to name tasks. This is only used by the tracing instrumentation. So you need to enable the tracing feature as well. I mean, you need that anyway, but console subscriber will enable it for you because features are additive in Rust. It's really useful in Tokio Console. So let's have a look at that. Oh, no, let's look first at how you do it. You take your task builder and you call new, of course, and then you name your task. This isn't a static string, so you can give it dynamic values, and then you spawn your task like normal, passing it a future. So now we've got some very, very creative names for our tasks, but this does come in like really handy when you're debugging stuff. So you can scroll through the tasks. You can use the arrow keys. You can use J and K as well because everybody uses J and K, right? And you hit return on a task and you get the task details. So up here on the top left, you get the details which were mostly already available in the list view. But then we have a lot more information about wakers over here on the right-hand side, the current number of wakers. It's important that that number is not 0. The number of times that the wakers have been cloned and dropped, and the number of times that the task has been woken and when it was last woken. And you don't see it here, but if a task gets self-woken, that will be listed separately as well. Down here, we have a histogram for the poll times. So this is timings for how long the task took to be polled across its lifetime. And then the same for the scheduled time. So this is useful if you sort of, again, we don't see it here, but there's an upper limit on the time we'll collect, and then we just collect outside values over 1 second by default from memory, but that's also configurable. If you make it longer, then your histogram data structure gets bigger. So maybe you want to make it shorter, and then you use less memory. And down the bottom, we have all of our fields. Again, if there's longer fields like the blocking function signature, then it's probably easier to read it down here. Oh, a wild warning has appeared. I forgot the red box. Okay, up here, you can see there is a warning. It says this task has lost its waker. It will never be woken again. And this is corroborated by the fact that there's a 0 here, which is a bad thing. Oh no, I did write a red box. Look at that. So, Tokio Console, and this is in the console itself, has lints. It can detect suspicious behavior, and the detection is powered by lints. Currently, the lints that are available are lost waker lint, the self-wakes lint, and the never yielded lint. There will be more to come. Writing a new lint is actually a really great beginner task as well, just saying. So, our lost waker lint. This will tell you, so an idle task, if it returns, a task after returning pending, which it will then be idle, must be woken. Otherwise, it will never be polled again. This is the secret source of async. This is done via the waker. If the waker isn't held onto, the task never gets woken again, and that task will sit there idle forever. So, how could that happen? I'm implementing my own future. You can do this without implementing your own future, but it's more obvious. So, I'm implementing my own future. I want to sleep once and then return idle pending for some reason, and then when I get woken again, I'll just go, hey, yeah, I've slept once already, I'm ready. So, what that means, I'm grabbing my, my sleep here, and then I'm polling it, and if it's ready, then I'm setting slept true, but we're not keeping sleep anywhere. And if I drop this sleep future, it's the one holding onto the waker. I'm not holding onto it. Yeah, and then we end up in this situation where the task has lost its waker. It'll never be woken again. This is a pretty contrived example, although to be honest, copying and pasting your first code to write a future, it's not that unlikely that this is going to happen. But there are plenty of other examples where this might happen. So, self-wakes. A task may self-wake. So this is done sort of manually by you by calling yield now from Tokio. But self-waking too often might indicate a problem. For example, Tokio's co-op budget will force a task to wake, so self-wake, forcing it to yield in certain circumstances. This indicates that the task would otherwise block. So maybe you should consider moving this outside the runtime. Here's an example which is, yeah, okay, maybe less contrived. So here is a process or retry implementation which pulls something out of a queue. So it's a channel. It checks whether it's ready. If it's not ready, it does a little bit of work. This should be taking about 10 microseconds. That's not blocking. That's okay. And then it's going to put it back into the queue because it's not ready yet. If it is ready, then we'll process it. This takes 40 microseconds, which is a little bit longer, but still, in the realms of non-blocking. But the problem here is we might be keeping our queue always ready. If something else is injecting this stuff in, which we assume it is, we might be keeping this queue always ready. And that means that this await here and this await here will never actually yield back to the runtime because there's always space in the channel and there's always something to do. And this will end up in this situation where, look, lint, the task has awoken itself more than 50% of the time. It's awaking itself 100% of the time, which is more than 50%. And look down here at the poll times. We were kind of expecting that we were going to have either 10 or 40 microseconds in between await points. What we're actually seeing is we're more like 10 milliseconds, which is way too long if you want your async application to be responsive in a high throughput sort of situation. So again, this is something, hey, maybe you want to take this, loop, if it's going to work like this and either destructure it in a different way, throw it into, its own thread pool or something like this. And the final lint is never yielded lint. So this is a task that has never yielded to the runtime, and it's been running for more than 1 second. This task is definitely blocking. There's no questions about it. Move it outside the runtime. What might happen here? Look, we have an async function. It's going to do some pre-work to get our initial items, and then it's going to process them. Lots of await points. We shouldn't have a problem. How long does this take, though? So if we go and look in Tokio Console, it's never yielded. It's been running for 14 seconds. Okay, again, a little bit contrived. But this is the sort of thing that you might like, it's just a good way of highlighting that this task, and you'll see these warnings appear in the list as well. So you start seeing little warning icons next to your task in the list. It's a good place to start investigating if you're experiencing behavior that you're not expecting. So what have we learned about Tokio Console? It's built on the tracing instrumentation, which is already in Tokio. The console subscriber collects and aggregates information. Tokio Console allows you to visualize the application state, and it warns you about possibly incorrect behavior. I mean, you might want to do that. That's all, that's fine. You can ignore them. We don't have a way to ignore them. You have to do it yourself. Finally, last tool, task dumps. So this allows you to capture a snapshot of the runtime state, which is really cool. This idea was brought up by Jack Wren, again, the same guy from Tokio Metrics earlier on. It records a snapshot of all tasks on the runtime. Each task includes a backtrace from all the leaf futures. A leaf future is the topmost future on the call stack. It does require leaf futures to be instrumented. But otherwise it kind of works like thread dumps in Java, but for Rust, which is really exciting. There are some limitations that apply. I'll discuss them a little bit later on. So, also a little bit of extra config. We need this Tokio task dump config in addition to the Tokio unstable config. This is better than using features rather, because unstable features is not a thing that Rust has, and that means that once you create a feature, for instance, we have the tracing feature in Tokio, that basically leaks out into your public API, and you can never remove that feature, even if it does nothing. Again, I recommend putting this in cargo config instead of using the environment variable. So, how do we create a task dump? We take our runtime handle. We know how to get one of them. We call dump. This can take some time. It basically has to pause the entire runtime and poll every active task in a special mode so that it gets, so that it basically emits the backtrace back up the stack. Then we iterate through all of our tasks, and we can do something like print it out. You'll see the pretty printing is pretty nice, but you can get programmatic access to all of this information as well. So let's look at a simple one. Here is a task which sleeps for 100 milliseconds. That's all it does. It waits on sleep, and the backtrace will start at the inner pole. So we can see it down here. We get backtrace with the function signature and the location where that happened. You normally get much uglier locations for stuff from crates.io, but I manually edited that here. So yeah, normally you're going to get your full path. And here as well, actually. I manually edited this because it's a presentation. So what does that look like? A little bit simpler, right? We're in our dump sleep, which is my application in main, closure, because we're in async and we have closures everywhere. Then we're in poll on sleep. So this is sleep as a future, calling poll. And then inside that, we have a poll elapsed, and this is the final leaf future that gets instrumented. So something a little bit deeper. Inside our main, we are going to spawn a task. It calls and awaits an async function A, which calls and awaits an async function B, which calls and awaits an async function C. This is getting repetitive. C finally does something more interesting. It sleeps for 100 milliseconds. Again. And what you see here is a deeper call stack, but basically you see that we're running through each of these. Again, I've got a bigger version. So we have all of this closure stuff here because of the way that async awaits syntax desugars. That's why we have closures everywhere. But otherwise, just think, look, here's your function A, B, C, and then we're back down into sleep that we saw before. But sometimes you have more than one future that you're waiting on at the same time. For example, if you're using Tokio Select, then maybe you're awaiting multiple futures. Tokio Select will await a whole bunch of futures for you, but within one task, so not spawning them off onto different tasks. And it will run this block here for the first future that returns ready and matches a pattern here, which I haven't included, so whichever one comes out first. So here I'm waiting for a barrier. I'm sleeping for 100 milliseconds. I love 100 milliseconds. I don't know why. And we're waiting to receive something from multi-producers in consumer channel. This is what it looks like. this is just one task. So so here we've got our MPSC channel receive, here we've got our sleep, here we've got our wait. This is very large, it's too big to read, you're not supposed to read it, you're just supposed to look at it and go, ooh, big. And this is just one task. As you can see, the sort of current method of let's just print everything out to the console and read it, probably not going to fly. We're going to need, in the future, some more instrumentation which is built around task dumps, which allows you to navigate them and look through them sort of more. Right, now onto the caveats. Task dumps is work in progress. Task dumps was first released in Tokio 1.31, 32. We're on 1.34 now, so not very long ago. Creating task dumps is expensive. As I said, we pause the whole runtime, we run a special poll on every single task and record all of the output. So, you know, it's not something, you can't do this every 10 milliseconds and then produce a graph of the timings. It's just not appropriate. But enabling the feature isn't expensive. So this is the sort of thing, maybe not today, but once it's a little bit more sort of stabilized, this is the sort of thing that you can enable, leave it there. When your async application starts doing something really weird or hanging or, you know, whatever it is, you have some way to trigger your task dump, grab the output the same way that you would with your thread dump in Java, and you can grab the state of your application and then post-mortem it later. There isn't so much metadata available. Key for me as somebody who works a bit more on Tokio Console, task names and IDs aren't available yet. I mean, they will be. Function parameters are also not available. So these are the sort of things that will make it much more useful. And for weird reasons with respect to backtrace offsets, it's only supported on Linux at the moment. So what have we learned about task dumps? It's a new Tokio feature. It creates a snapshot of your runtime, the tasks, and it's useful for pinpointing stuck tasks. Right, now we're getting to the end of the presentation. I'm doing okay. Well, no, I'm going over time. Oh, look, game over. There we go. No, it's okay, I'm almost done. So where are we up to and what's next? So quick summary of what we've discussed today with respect to the 3 different tools, the level of detail that they provide for you, and whether or not I personally, as somebody who, you can decide how much you trust me, would use this in production. Metrics gives you a low level of detail, although it's a hell of a lot more than none, and I would definitely use it in production. I do. Tokio Console provides a medium level of information, so you're still seeing really things aggregated on a task level. Careful about using it in production. The console subscriber today uses quite a bit of memory per task, so if you're spawning hundreds of tasks, even if they're very short-lived, you're churning through quite a bit of like memory allocation, so like up to you what your application does, whether it's worth it. Task dumps gives you a really, really high level of detail. I wouldn't use it in production yet. As I said, I really think that task dumps is something that we could have like enabled to be running in production to use when there's a problem. But maybe not yet. It's up to you though. You're all adults. So what about the future of these tools? So for metrics, which is probably the most stable of the 3, probably be interesting to see some additional metrics. I think that today we don't have anything measuring, for example, the last in, first out slot, which is used for optimization when passing messages between tasks. And I'd love to see simpler collector integration, which I've mentioned at least 3 times so far. Tokio Console, I'd like to see more lints and more usability features. So filtering, for example, because if you've got hundreds of tasks, finding the one you're interested in is sometimes difficult. Custom span integration would be fantastic. I can imagine that you could instrument your own tasks with spans and then get timing information from that, but on a per task level, which is actually probably not as hard as it sounds, although, yeah, I might be wrong about that. And task dumps. So task identifiers is the first thing I'd like to see. Task ID, the name. So you see these in Tokio Console. It would allow you to run back and forth. More backtrace metadata and obviously more like support more platforms. Finally, the ecosystem, I'd love to see better integration. So metrics and task dumps inside Tokio Console would be fantastic. Or together elsewhere, I don't care. Standardized runtime instrumentation would also be really cool. So you can imagine you could actually standardize this instrumentation, so you could put it in async standard or small. I don't know about Embassy. Embedded, maybe it's a little bit heavy for that, although tracing can run in embedded, so maybe you just have to post-process it. And you're the future. All of these tools are open source. Many are developed in maintainer free time. If you'd like to help, come join us on the Tokio Discord. You can contact me by the other stuff, but also if you come into the Tokio Discord, there's a console channel and a Tokio channel, and you'll find Alice in the Tokio channel, like far more hours than anybody should be awake. Fewer hours of the day, you'll find me always in the console channel, often in the tracing channel as well. Yeah, so if you have a question or you want to help out or just want to chat, that's a great place to find us. Finally, to sum up, async programming can be hard. Instrumentation of runtimes can offset this difficulty. There are many options to see what's going on in your async program, but we're not all the way there yet. There's still a way to go. Thank you very much for listening.
Okay, thank you. Yeah, before Q&A, I got a few announcements, which are important, so I got to do them very fast now. The first is from security, and they ask you to please always wear your badge, because for security and management reasons. Then the other one is that Mario Villar, which has a talk at 2:30 p.m., will not be here for health reasons. So we can have more lightning talks starting from 14:20. So there is a big table where you can sign yourself for the lightning talks. We have more than an hour for that, so right? And nothing else. So questions? Thank you.
Okay, from a Rust newbie perspective, I find this a little bit overwhelming. I mean, with unsafe, you can actually choose to not use unsafe, but here, depending on the task, you probably have to use async. And then, is there any plan to, for example, do so that when you run cargo test or something, this it would already tell you at that point that you're being stupid, instead of going to all these different tools and having this long process of finding out just how stupid you were.
That was basically the topic of Antonio's talk yesterday. So I believe all of these talks are going to be recorded. I would definitely check that out. He talked about deterministic testing of async programs. And that is a fantastic place to start. So start with the testing. Try and catch the stuff there. These are tools that will help you when you don't catch it or when you don't bother. So.
Okay, thanks.
Very nice talk. So you showcased options to take some level of, well, to capture some introspection data about Tokio, either using task dumps, task monitors, so on and so forth. All these options seem to rely on the assumption that some part of the application is still responsive. Like there is still something you can ping that's gonna go and take that task dump and push it out to you. But let's make an example of a current thread, Tokio Runtime, which is running on a single thread. You have some task which is blocking, is not yielding to the runtime. What options do you have at that point as the operator of that application to actually realize what's going on?
So
if
that's
any.
Part of the advantage of the fact that the console subscriber server is on a different runtime. And the tracing instrumentation that you have, so basically with Tokio Console, it's using tracing. Tracing is, basically you're going to stop getting data. If you're really blocking everything, you're going to stop getting data from your runtime, but the server is still going to be responding. So you still know that something is going on.
I know it's dead, but I don't know much more than that, do I?
I mean, but you know, for example, what task was running at the time that everything stopped. Because that's, I mean, let's say your task is blocking, stops responding, whatever, but while it's running, then you know that that's the task that's running. Because we've collected the information beforehand, we know when the task polling started. And from there, we can say, okay, this is a problematic task. And Tokio Console will give you a little bit more information, but at that point, you really want to perhaps revert back to something like task dumps to say, okay, what are the futures which are running? Like, what's the future hierarchy on that task? Which, look, if your entire application is not running, like if nothing's running, then that's a bigger problem, right? But let's just assume for a moment that it's just your runtime, even if it's current thread runtime that's not running. You're going to need some extra way to come into that to be able to say, right, now, I don't know, like a control C and like a sig int or something, and now produce a task dump, which you're doing synchronously from somewhere else. Or, I mean, look, you can still go back to the debugger, right?
Yeah, I mean,
you're going to get some information depending on, you know, level of debug information, whatever. But if you've got something that's stopped and you know the task that it's in, that gives you a little bit more context to then go to the debugger and make sense of the stack trace, for example.
yeah, I guess my point of view is more around application not running locally, actually running in, you know, production servers where a lot of these options are not necessarily available. So I guess the TLDR, the answer is you need a background thread somewhere that you can go into.
Yeah, I mean, Tokio Console gives you that.
Questions?
Hello, thanks for the amazing talk. You just said Tokio Console gives you that, but you said beware about using Tokio Console in production.
I said it gives you that. I didn't say you should use it for that. No. So the console subscriber has overhead. It runs inside your application. It offloads a lot of the processing, like what it can, to the console subscriber. But in order to not saturate that communication channel, it aggregates things locally. It's producing histograms locally rather than sending that stuff across the wire. Maybe there's another way to do that. You could probably envision a way that you're sending like a lot more data over the wire of raw data and then processing it elsewhere. But at least for now, that's the model it's following. And the big problem with memory consumption is on these histograms. So I might be way, way off here, but the number I have in my head is 10K each. So that's 10 kilobytes per task, which if you have a lot of tasks, and even worse, if the channel that we use to pass the tasks from your runtime to the console subscriber runtime starts to back up, that memory starts to like really grow. I think there's some optimization there because a lot of tasks aren't long-lived. You could store, like not store a histogram, store the last 10. Once you run out of space, then create a histogram.
Perfect. You just answered the question I didn't make, and I was going to make, because essentially I observed memory consumption in the gigabytes range when my tasks were waiting for, let's say, external things that didn't happen, and I had tasks by the thousands.
Yeah.
And that was just what the server needed to do because it had thousands of requests, and well, that was it. So
yeah, I would suggest that you're probably also, and we don't have instrumentation around this yet, but we need it, like internal instrumentation about that queue that's passing new tasks from your runtime to the subscriber runtime, because at the moment we're not very efficient about emptying that channel, and that's when the memory consumption starts to go whee, because it just backs up, and you've got these histograms which have been created with one value in them. That you're passing along, and that's a problem. It's on the to-do list.
Okay, perfect. Thanks.
Hi, thanks for the talk. Two related questions. You showed this table of what you can actually use in production. And from this table, you can see it's mostly metrics. So my first question is, some of the warnings you showed from Tokio Console, is it possible to get those somehow in production, that you can get some of those warnings to, I don't know, log to a third-party service or something that you can then observe later? That's the first question. The second question is related to metrics. We gather all of this data, and there's like pretty graphs of it, but what are the actual conclusions we can make from that?
Okay, first question first. Not really today. So I think this is something that providing options to make this more production ready is a possibility. Certainly what you can do today is run like console subscriber without anything connected to it, and you can set a very short duration for the tasks that you want to keep the information about, and then it doesn't use so much memory. But you've got to connect pretty quickly after you've got a problem, otherwise you will have lost the data that you're interested in. So yeah, I mean, there's space to explore how to improve this and how to make it, let's say, a little bit more production readyable to debug. And the second question was about metrics. So I would encourage you on the task monitor side, so the task metrics, go and check out the Tokio Metrics crate. Look at the task monitor documentation. As I said, there is a fantastic like debugging scenario which describes, I mean, there's documentation on all of these metrics and what they mean, but this really gives you a step-by-step of like, hey, these are 3 questions you can ask. You can look at these metrics to say whether any of these are yes or no. The runtime metrics, to be honest, to have the same for the runtime monitor would be fantastic, but nobody's written it so far.
Right, thanks, that's perfect.
Okay, last one.
You talked a lot about exporting all these metrics because it's expensive to hold them on the system itself. The tracing OpenTelemetry crate has now a metrics feature to activate OpenTelemetry metrics that actually allows you to export everything over UDP and have the metrics data collector doing all this stuff. Have you thought about maybe this?
I think so there's 2 different things here. One is the metrics which come from Tokio, and those are not expensive to keep around. I mean, like the metrics from Tokio itself and the ones produced by the Tokio Metrics crate, they're fine. Like that's production ready. The stuff that's expensive is not metrics, it's the basically aggregation of and the raw tracing data. And if you turn that into metrics before it hits the console subscriber, you don't have enough information. So what we are basically doing with the tracing data is saying, right, a span started, a span stopped. Like a task was polled, started, stopped, then there's a waker event. Did this happen within this task or was it outside this task? Then another span will start, and we have to say, okay, when a new, like a task, like the task span becomes active, which is when the task starts to get polled, we need to have information about when was the last waker, last time it was woken, the last time it was polled, and all of this information. And that's needed to do the aggregation. So you need that on a per task level. And you have to keep that on a per task level. If you aggregate those traces into metrics earlier, you lose the ability to do that. Yeah, I mean, I didn't show any of them. There is definitely space to basically have a better way to visualize task behavior from the raw traces as well, because stuff like most OpenTelemetry products, they're just not set up to plug the right things in together. You need, there's too much correlation, which is really specific to Tokio. So there's space to sort of be able to output this information in a stream that's maybe a little bit more a little bit easier to visualize. But it has to be a bit more specific to our use case, because I've tried just plugging this stuff into Jaeger, for example, and you just lose the connections. Like you can't connect when something's being woken to the task that woke it and the task that's waking and stuff like this. So some of that information doesn't even make it to OpenTelemetry, which is part of the problem, because we depend a lot on the span ID in tracing, and that's an internal ID, which the subscriber has access to, but generally isn't forwarded along. And that makes using it with OpenTelemetry really hard. You'd have to put it somewhere else, I suppose.
Okay, we got time for another question. If you want to. Anyone? Questions? Yeah.
Hi, thank you for your talk. I just wanted to ask a bit more concrete question regarding the task names that you mentioned in Tokio Console. Yep. Is it a way, for example, in Tonic that uses Tokio heavily, to have somehow to enforce him to use some of Tokio of task name for specific task, or am I just like in the hands of third party and implementer to say, okay, it will have name or not?